Let's jump right into this explainer by stepping straight into the nerve center of the GF-12000 drillship. Picture this. You're standing inside the bridge's glowing dynamic positioning, or DP, control room. This is the human-machine interface layer that keeps a massive, 6-story steel drillship precisely on station over a wellhead thousands of meters below the surface, even while it's facing down heavy seas and screaming winds. You have these operator consoles humming away, and standing right beside them is a vertical alert light column. When that light column flips to red, every single hand on the drill floor knows exactly what it means without a word being spoken. Get ready, because position may be lost. Today, we're going to break down how all that redundancy and sensor data actually gets used by the operators to prevent that exact nightmare scenario.
You know, it's wild to think about how far this technology has actually come. I love this quote from a veteran offshore engineer recalling his early days working on drill ships. Back then, simply managing the dynamic positioning of a vessel required a mainframe computer that was essentially the size of a house. That immense bulk was needed just to process the basic sensor data and push out the thruster commands required to keep the ship from drifting off the wellhead.
Well, thankfully, those house-sized mainframes are a thing of the past. Today's DP3 systems pack exponentially more predictive processing power into highly compact setups that really just look like modest-sized desks. And because the GF-12000 is a fully certified DP3 vessel, it's not just one desk. There is complete end-to-end backup redundancy for every system, ensuring that a single failure can never ever bring down the vessel's station-keeping ability.
So how does this actually look in practice? Well, day-to-day operations rely on exactly 3 main dynamic positioning operator consoles. These 3 glowing stations are where the qualified DP operators actively run the system. They're monitoring the sensors and sending commands to the 6 massive thrusters beneath the hull. It's the primary interface where crucial human oversight meets full automation.
But here's the thing, because full automation always demands an ultimate fallback, there is exactly one physically separate backup DP control room, and it's deliberately located down on E deck, which is 2 full decks away from the primary bridge.
Why the physical separation? It's an absolute DP3 requirement. This guarantees that if the primary control room is somehow compromised, say by a fire, a flood, or just a total localized system failure, qualified operators can rush down to EDAC and immediately take over. They have an entirely independent equipment setup just waiting for them. This protects against the loss of the primary bridge, and most importantly, it ensures unbroken station-keeping oversight. When you've got a live, well-connected to the ship via a rigid marine riser, an uncontrolled drift-off isn't just an inconvenience, it's a catastrophic well control event. This backup room is exactly what prevents that.
Okay, let's talk about the actual brains behind these consoles. A brilliant piece of software known as consequence analysis. Think of this as a predictive shield. Rather than just sitting there waiting for an actual failure to happen, consequence analysis is constantly running these background what-if simulations. It's looking at the current thruster allocation, the power loads across the engine rooms, the environmental forces hitting the ship, and it's testing hypothetical worst-case failures against them in real time.
In fact, the system is constantly asking itself one very specific question every single fraction of a second. If the most loaded thruster or generator failed right this second, could we still hold position? Imagine the vessel is fighting a heavy broadside wind and one thruster is just working overtime. The consequence analysis software isolates that specific thruster and mathematically kills it just to see if the remaining 5 thrusters and the remaining electrical generators have enough reserve capacity to absorb that shock and keep the ship safely over the well.
It's essentially the mathematical logic of survival, playing out in a continuous 3-step loop. First, it calculates the current system state. Second, it subtracts the worst-case single failure, like losing an entire engine room or that hardest-working thruster we just talked about. And third, it confirms if the resulting capacity is greater than or equal to the absolute minimum capability needed to hold position. If that equation ever starts trending toward a no, the system knows there's a serious problem before a single piece of hardware actually breaks.
So how does all that complex predictive math actually get communicated to the crew? Through a beautifully simple, unmistakable traffic light alert column. Green means normal, your full redundancy is completely intact. Yellow means caution, you have reduced capability and thin safety margins. And red means critical, you are facing a potential loss of position and an emergency disconnect from the well might be imminent. Like we mentioned earlier, when that light hits red, the entire drill floor's mood shifts in half a second.
But here is a massive insight that honestly even some junior engineers completely miss. A yellow alert, it often happens with absolutely 0 broken parts.
A yellow caution doesn't automatically mean a generator tripped or a thruster snapped. It usually just means your power loading has become uneven and risky. It means your safety margin against that hypothetical worst-case failure has thinned out. The system is essentially tapping you on the shoulder saying, hey, I'm fine right now, but if my biggest engine fails in the next 5 minutes, we won't survive.
This requires a totally different operational mindset. Think of consequence analysis and the yellow alert exactly like a smoke detector rather than a fire alarm. A fire alarm tells you the fire has already started, the damage is done. A smoke detector, on the other hand, tells you conditions are trending toward a fire, giving you the early warning you need to intervene before the flame ever appears. Consequence analysis is the ultimate smoke detector for a drill ship's DP system.
So, what do the operators actually do when that yellow caution lights up, but there are no active fault icons? Well, they have to act immediately. First, they acknowledge the alert. Second, they review the power and thruster load distribution across all 3 engine rooms. And third, they proactively rebalance the generators and thrusters. Maybe you've got 2 generators running near max capacity in one room, while a third room's generator is just sitting idle. By rebalancing that load, you regain your safety margin, and you turn that yellow light right back to green, all with 0 physical faults ever occurring.
As we wrap up this explainer, I really want you to take away this one critical rule. Treating a yellow alert as routine background noise is, hands down, the fastest way to hit a red critical status. It's actually one of the most common human factor causes of escalation out there. The drill ship is smart enough to run continuous consequence analysis and predict its own failures before they happen, but human operators still have to heed the warnings and take action, which leaves us with a pretty fascinating thought to consider. If a fully automated system can perfectly predict its own vulnerability, is the weakest link in DP3 redundancy the computer or the operator who chooses to ignore it?